Hello, everybody. Thank you so much for joining our webinar today. We're really excited to show you the work of Dr. Erkan Asik at the Eindhoven University of Technology. This webinar today is part of our series of webinars that we're holding, which is focusing on AI workflows for patient-specific device development. My name is David Harmon. I'm a business development manager here at Synopsys Simpleware, and I'm going to introduce the subject for you and also provide an outline of what our software does and what sort of technologies Dr. Erkan Asik is taking or making most use out of for his work, what part of the Simpleware software he's focusing on. So the webinar today is really going to look at how Eindhoven University of Technology, Maastricht University, particularly the medical center there, and also industrial partners, DSM and Chemalot Insight, have been focusing on implant designs and researching implant designs using patient-specific knee models and analyzing the effect of the implants that are being investigated on joint mechanics in these patient-specific knee models. So I think that's all I have to focus on at the moment, but Erkan's going to take you through the process and how he's used AI-based technology that's held within the Simpleware software within our module AS Ortho to rapidly produce segmented models of the knee from MRI data, and how he's then used these models within the software to produce finite element models alongside CAD designs of the implant to take through into simulation and obviously investigate these joint mechanics. But as I say, I'm incredibly honored to have Erkan with us presenting his work and showing his use of the Simpleware software in not only automated segmentation, but also simulation or generating models for simulation too. So that's a bit of an introduction, but thank you once again for joining us, and I'm really looking forward to getting into this webinar. Initially, I'm going to just introduce the Simpleware software and who we are as a company quickly, and then I'll pass right over to Erkan to take over the main content of the webinar today. Right, so moving on, so Synopsys Simpleware. The Simpleware product group is really a business unit within Synopsys, and our focus really is the development of 3D image processing software and very good quality 3D imaging processing software that, as you might imagine. Our focus has always been creating or being able to generate a software that allows our users to take image data, 3D image data, and go through the process of generating models for a variety of different outputs, whether that's simulation or CAD design, and outputting those formats to the variety of different softwares that you need to use to carry on your workflow. So our focus is generally the segmentation, image processing, and the model generation. So the meshing process has always been a challenge, and that's where we've strived for greatness. So alongside that aim and our goals, we have a dedicated sales and support and service team around the world. We've headquartered in the UK down in the southwest in Exeter. And we have a variety of different support engineers here helping people all over the world, and that's mirrored in other regions as well. So we have a global presence and we work with customers and applications in clinical, life sciences worlds, and also materials and manufacturing and more. Really, we follow the use of image data through the different industries and apply our software to help people generate models and statistics and measurements and meshes for simulation from that data. So having a look at the different applications for our software in life sciences and clinical applications, obviously on the left-hand side, we have more of the kind of life sciences applications in terms of protective gear. So what we're showing here is that our software can be used to generate the models from image data, from MRI or CT data, for example, in this case, in the top left, the head, and then you can use our software to bring in CAD designs as well. And Erkan will really focus on that later to show how he's merged the worlds of image-based models and CAD models and then taken them all into simulation too. But kind of in parallel to that, we also have applications, as you might imagine, in looking at wearable electronics, looking at models from image data of people's anatomy and how they interact with these wearable technologies and electronics, the same with shoes. But then when we're looking on the more clinical side, on the right-hand side of this image, you can see that we focus on looking at how implants interact with the human body, and that's really the focus of today's webinar, and that's where Erkan is going to take you. But also looking at physiological simulation of flows, for instance, in this case, how flows interact with the human body and the geometries present there, and then also preparing different models for 3D printing. You can see in the bottom right-hand corner there, so this is a mandible case, but the world of 3D printing is also open to us because we can create models from image data and then prepare those and really optimize those for 3D printing using our 3D printing toolkit and our segmentation strategies to provide the different components or regions of interest within that model. So moving on. With those applications, we have a number of different technologies within our software, and these range from pure import technologies where we're looking at visualizing the volume data of the image where no image processing is required, and we can do that with 3D data, and also 4D data where there's a time step involved in, or multiple time steps involved in the data. Then once we've imported it, we can go through the segmentation process. And as today's webinar, we're focusing on automated segmentation, so you'll see some of that capability. But we've also got more manual techniques and in the interactive techniques that you can adjust. And so we can go through that process to create the regions of interest for us that we're interested to research. Then we can go through the process of measurements and analysis, bringing in CAD to the image data to look at the interaction of implants, for instance. You can see that on the right-hand side there. And then right at the top, you can see our capabilities for the model generation. So we have a wide array of different model outputs and technologies that involve us creating models from the image data. And that's where we have a lot of experience and development creating very good quality models for simulation or for design from the image data, the creation of the proper surfaces and volumes for those applications. And then kind of underpinning all this, we also have the capability to script all of the capabilities within the software so that we can provide a great deal of automation. And you can interact with this script in various different languages, Python being the focus, and I am Python, for instance. But to give you access to that, if you don't necessarily have the skills currently to write the code, we also have macro recording functionality and ability to convert our log, our recording of your actions into the script so that you can bring those scripts into your work life. So that's the introduction of the Simpleware software. I hope you have a good understanding of what we can do. I'm now going to pass on to Dr. Erkan Asik. So thank you very much, Erkan, for joining us today and being willing to show your work. It's very exciting, and I'm really looking forward to it. So Dr. Erkan Asik, he's a postdoctoral researcher in the research group Orthopedic Biomechanics of Eindhoven University of Technology. He works on designing focal resurfacing implants for the knee joint in close collaboration with Maastricht University Medical Center, but also of course, the industrial partners DSM and Chemelot Insight. Erkan has really specialized in damage and failure under mechanical loading and understanding the relationship between microstructures and mechanical responses. And within his research, he's obviously done a lot of his qualifications within the material science. So he has a BSc and MSc degree in material science and also holds a PhD in mechanical engineering. So at this point, I'm going to pass over to Erkan to take over and present his work within the project and show you how he's been using the automated segmentation capabilities within the Simpleware AS Ortho module and take those through the model generation process using FE and also CAD integration using the CAD module to produce the models required for simulation and understanding the interaction between patient-specific models and the CAD designs of implants that are being researched. So thank you very much.
Thank you, David, for the introduction, and welcome everybody to today's webinar on improving patient outcomes with patient-specific knee models. In today's talk, I will introduce the SciCap project, give a description on how we are using the MRI knee data to generate finite element models. Then I will give some remarks on the finite element models and finalize the talk with a summary and conclusions. Before we start, I would like to introduce the project partners to you. The Camelot Insight is the Roof Institute which brings together public and private partners. DSM is the polymer manufacturing company. Uh, University of Maastricht and Technical University of Eindhoven are the two universities involved in the research. The main aim of the SciCap project is to develop a non-resorbable implant for treatment of cartilage defects for specifically middle-aged patients. We focus on middle-aged patients because currently there is a treatment gap. For younger patients, treatments based on the regenerative capability of the tissue work quite good. While for the old patients, uh, there is only chance to go to a heavy surgery. But for the middle-aged patients, both methods are not as successful as their own age groups. As a SciCap uh, project, we are working on developing focal knee resurfacing implants to bridge this gap. By this way, we are aiming to slow down or stop the degeneration of the cartilage health, and as a result, the patient may never need a total knee arthroplasty. There are already some available implants in the market. These are Hemicap, Episealer, and Biopoly. The first two of these implants are fully metal, while the Biopoly implant has a metallic stem with a polymeric top layer. Alternative to those implants, SciCap project or team suggests a two-layer fully polymer implant, as you can see from the schematic representation here. The top layer of this implant has mechanical properties close to cartilage, while the bottom layer has properties close to bone. The elastic modules of the bottom layer uh, can be tuned in order to prevent excess micro motion, which can lead to loosening of the bone. The SciCap implant has some advantages. Since the mechanical properties can be tuned, the implants match better with the mechanical properties of the native tissue. Secondly, the implants are not patient-specific. This gives us the opportunity to shorten the waiting time and have a lesser or less lead time, as well as producing more affordable implants for the patients. Apart from these, the implants are also MRI friendly since they are polymeric in nature. And this gives a quite nice advantage because the cartilage quality can be tracked even after the, the surgery, which is not an option for if you have a metallic implant. And finally, in the future, if the implant needs a revision, it's easier to cut or remove the polymeric implants from its position. Now we can come to the point on how we use the Synopsys software in our work. Currently in the project, we are in a stage where we need to develop knee models in order to see if the implant is positioned correctly, is carrying enough load, or during the walking or other activities, the implant is not overloaded. The generation of the 3D models for finite element analysis involves 4 steps. First, of course, is the acquisition of the MRI data, but this one I will not uh, go into deep in here. The second and third steps can be done in the Synopsys software, and they are segmentation of the knee and placement of the implant. And finally, after placement of the implant, one can generate 3D geometries and apply loading and boundary conditions to the geometries. The automatic segmentation toolbox of the Synopsys software generates the segmentation masks, as you can see here. These are mainly the patella, tibia, tibial cartilage, femoral cartilage, femur, and fibula. Apart or in addition to these masks, the Synopsys software also recognizes some landmarks, and one of them is quite important in the simulation of the gait cycle, and that one is the femoral epicondyle center. In addition to the automatically recognized masks, in order to do the simulations, one also needs to segment the meniscus manually, which is not automated up to now. After the segmentation, the segmented masks used to generate a 3D model. And in this model, we can also use the location of the damage, cartilage, and the implant. And we can modify this 3D geometry to incorporate also the implant. After the modification of the geometry, you can create a finite element model mesh within the Synopsys software and export it to your uh, finite element solver in terms of an STL file, or if you are using one of the uh, ones from the list, like Abacus here, you can directly export the input file to Abacus. Here we can see the procedure described previously with the arrows. On top is the 3D image showing the femoral side of the knee, and on the bottom is the relevant, or is the one of the slices and the relevant mask. And if we can locate an area, or if you locate an area is damaged, then we can use this area to create some Boolean masks in order to create a cavity in the shape of an implant. And during this operation, it also updates the mask automatically on the go, which is a nice feature. And later on, you can also uh, position the implant to its relevant place. And from the slices, you can also check if the implantation position is uh, accurate and proper. From the previous simulations, we know that placement of the implant plays a crucial role on how the stresses are generated in the joint during the motion. For example, if you have a protruding edge, this will cause an increase in the contact stresses in the tibial cartilage when compared to the healthy version. On the other hand, if you have an implant which is implanted too deep, then this will result in implant not carrying enough load and increase in the contact stresses of the femoral adjacent femoral condyle compared to the original case. Here you can see the imported 3D models in the abacus. In the cross section, you can see the position of the implant. Also in the frontal section, you can compare, you can see the implant's position. For the finite element simulations, we are using kinematic-driven boundary conditions, and then these boundary conditions are applied to the femoral epicondyle center, which was identified by the Synopsys software At this location, you basically apply load, flexion, extension, rotation, internal, external rotation, anterior, posterior translation, and medial lateral translation. In these simulations, we also leave valgus rotation free so that the knee aligns itself. Apart from the boundary conditions to the reference point here, you also need to fix the bottom of the tibial cartilage and the meniscal horns. The boundary conditions that result in the motion of the knee can be seen here. These are not patient-specific, but they represent or they are an average of a human population while walking. Those conditions basically represent the stand phase of the gait cycle, which is important for us since it is the phase where the knee joint is loaded. And after this uh, position, as you can see in the swing phase, the blue leg just swings to the forward and gets ready to carry the load again. As a result of the boundary conditions, we observe the following motion in the joint, and here you can also see the implant. In a side view of this motion, we can also see the locations where the implant is articulating against the opposing cartilage or the meniscus. Here we can go one step further and check the stress distributions in order to identify at which position or at which phase of the stance the implant is loaded the most. And what we see is that the stresses are higher at the 0.6 of the stance phase, which is the transition from the mid stance to transition phase. And if we analyze the cross sections at that instant, we see that there is more uh, load or stresses concentrated at the back of the implant, and in the lateral medial axis, the stress distribution is more homogeneous, even though there's slightly more stresses towards the center of the knee. We can also compare the stress distribution at this instance between the knee model with the implant and then the knee model with original geometry without an implant. What we can see is that the original geometry also has some stress intensities at the front side of the implant, at the anterior side, whereas the implant doesn't. This may suggest that implant can be slightly tilted so that this front part also gets loaded during the motion. In order to get more information, we can also compare the contact stress intensities. Here we see that the femoral cartilage with the implant has slightly more stresses compared to the uh, original case. And then the higher stress intensity region also corresponds to the higher stress intensity region in the meniscus. And if you check the stress intensities in the tibial cartilage, we see that the tibial cartilage is loaded less in the implanted version. But I also must here tell you that these differences are less than 10%. So this may suggest that the implant position is acceptable. To conclude and summarize, in today's talk, I introduced you a composite stem PCU implant, and I showed a workflow to generate finite element models by using the MRI slices and the Synopsys software. And then I also showed how you can use the results of the finite element models in order to get an idea on the suitability of the implant position. Thank you all for listening. I think we will have some time for questions and answers.
Thank you ever so much, Erkan. It was a fantastic presentation and really interesting to see your use of AS Ortho and the meshing capabilities. I was thinking this is exactly where we saw the use of our modules and how we wanted them to be used in research and industry. So it's great to see you making use of that. Thank you once again, and thank you everyone else for attending and watching the webinar today. If you're interested to see more and try the software for yourself, then we have a 30-day free trial. So you can go to our website and request the trial. We can also arrange demonstrations for you. I think that's obviously the best place to start for us to show you what can be done in the software, and then we can point you towards the trial so that you can have a go yourselves. If you're looking for something a bit faster, perhaps you can go to our website and have a look at our resources. So we have a lot of videos, on-demand webinars, and different data sheets that you can have a look at yourself. You can see the website for that here, www.synopsys.com/simpleware/resources.html. And then, of course, please feel free to contact us on these email addresses you can see here. We would be more than willing to hear from you and to start a conversation about where you can implement the software. So I think without further ado, we'll open up the Q&A. But before we do that, I'll just say another thank you to Erkan. It's really been great to see the work. I'm really happy that you were able to join us today and present the work that you've completed. So I look forward to seeing how it progresses even further in the future. And thank you everyone for attending. So we'll open up the Q&A now, and I look forward to speaking to you.
Okay, thank you very much to David and Erkan for both of their presentations. So we have a few questions that have come in already. So we'll get started with those immediately. So the first one, how reliable is the automated segmentation capability of Simpleware? And how much manual work, such as the meniscus segmentation and any tidy up, is required in order to obtain an adequate model for simulation?
So I think I can give a quick answer to that. So as David described, my background is not like directly from a medical field or MRI field, but I think it works quite good. And then also the segmentation takes like 20 minutes. It is usually, I think, reliable. We also checked it with a couple of doctors, so they were also happy. And manual segmentation of the meniscus is also, for me, it takes probably quite longer than someone with a more trained eye, but that's also quite fast. So I can do all the segmentation within an hour. And from that point, passing to finite elements is also like with a little bit smoothing and everything, like 45 minutes, an hour more. So in 2 hours, you can just have the finite element model running.
That's fantastic to hear, Ken. Thanks for your feedback there. Just to add to that as well, we've really worked hard to make sure the segmentation, the automatic segmentation tool takes in to account as much variation as possible. So we've done an awful lot of training there and work to ensure that. Of course, there are cases where it won't work perfectly, and that's a given. But what we do expect is that the tool will give you a really good starting point for you to complete that segmentation. So it'll take a lot of the effort out, or at least some of the effort out, so that you can continue on that process and save some time. Also, it's very because of its automated nature, it's very dependent upon the hardware you have. So having access to a CUDA-enabled NVIDIA GPU is very important, and with the right specifications, you can get the runtime of the tool right down. So the scalability of it is very different from manual segmentation. So that's my points to add to that. But yeah, just to answer the question again, it's very dependent upon the data you bring in. There are specific types of data that it works with ideally, and that the tool has been trained with. So I think the best way to get to grips with that is to look at our data sheets and understand exactly what it's designed for.
Okay, thank you both. Leading on from that a little bit then, can you tell us a bit more about what manual tools and approaches were used to segment the meniscus?
So in that part, you can use like, how to describe it? Like some paint brushes or like fill masks and those kind of stuffs. So you can just select a region and it just creates the mask later on. So that is the main tool that I am using there.
So yeah, I guess that was a bit of a learning curve for you, Erkan, getting to grips with those new tools too. But so there are different tools that are available there. So obviously, when you get to the very manual nitty-gritty bits of segmentation, those painting tools come in very useful. And then we've got all sorts of tools for extrapolating and interpolating between slices and doing a variety of different things. The tools are quite extensive there.
Okay, great. Are you able to tell us a bit more about why the specific implant geometry was designed and what problems it hopes to solve?
So we are hoping to solve the problem of osteoarthritis in middle-aged patients because of the problems I described in the slides. And the geometry of the implant actually has like a couple of design features where we want to mimic the curvature of the knee of a population of an average population as much as possible. And then we also don't want to remove a lot of bone, so we are also limited with that. So it's also why it's like a, let's say, a mushroom, but not like a cylinder that's going into the bone. So that's the main reason why we have that shape.
Excellent. What is the segmentation processing time like with AS Ortho alone?
So that one finishes like in 5-6 minutes. That it segments the femoral cartilage, tibial cartilage, and patella, and fibula, of course. And then just screening and going through all the masks again, like takes another 10-15 minutes, I think, just to make sure that the segmentation is okay.
Okay, great. This one's a bit more focused on the simulation itself. So with the work placed into the creation of patient-specific models, have you considered increasing the accuracy of the system by including patient-specific gait kinematics and ligament pre-stress, etc.?
Yeah, so we are also considering those. For these simulations, I tried to be as generic as possible. So it's let's say, anonymous MRI data with anonymous or average gait cycle, but of course, including like ligaments as springs, or including like the patient-specific gait cycle would play a role in the future.
Just
Okay,
thinking. Sorry, go on, Matt. Sorry.
No, go ahead, David, if you have something to add.
I was just referring back. I think I just wanted to add another point that's just come to mind in our discussions, and that's Erkan, you've obviously been really focusing on the segmentation of the knee, of course, and the implant. But one point that's perhaps of interest to the audience is the tool also includes capability to segment the hip from CT and also the ankle from CT and also knee from CT. So I think obviously you've been looking at MRI, Erkan, so the tool also works with CT, but with the CT aspect, the cartilage isn't so prominent in the image data, so we focus on the bones in that case. Mm-hmm. But one question for me, Erkan, do you also have CT data that you're looking to analyze too?
Not actually, because we need to monitor the health of the cartilage, so we basically by default have MRI of everyone. In that case, we don't have the CT scans.
Sure. Okay.
But I think in that case, yeah, excluding the cartilage, I think that would also work quite good.
Yes. Yeah. Okay. Yeah. And also the landmarking. We mustn't forget the tool has automated landmarking in addition to segmentation. Do you use that functionality currently, or is that something that's still?
The landmarks I use, especially for applying the boundary conditions. So I need to find the epicondyle center, and then the software directly gives the medial and lateral epicondyle center. So I just need to take the average to find the central part.
Excellent. That's good to hear. Okay, Matt, sorry, I hand back over to you.
Yeah, no problem. So just one last question then to wrap up on. To what extent do in silico trials like these add value potentially to improving patient outcomes? And do you envisage the usage of these in a more clinical setting in future? And what's potentially the kind of time span for that, and what improvements do you see that need to occur?
So in this stage, it is, I think, quite crucial to create a protocol for the surgery, so that you basically need to know where you should or how deep you need to implant the implant, do the surgery or drill the bone. So that's, I think, crucial. There may come a time when you have enough experience, so you can come with a number like it should be 0.5 millimeters deep every time. So if you can come to a point or an average number there, then you basically don't need to run all these simulations again. But otherwise, till coming to that point, I think we need to keep doing the simulations to find the best position of the implant.
And just from me there as well, with this sort of process, it holds so many possibilities for bringing in patient-specific data and even looking at using it in the planning procedures for individual surgeries as well, I imagine. And making, obviously the implant itself is for generic use amongst the population of the age deemed appropriate, but then perhaps positioning could be optimized per patient on a patient-specific basis and given the best performance with that.
Excellent. Well, that seems like a suitable place to wrap up for today. So thank you to everyone who submitted questions. Those of you who didn't have your question answered live, we will also get in touch with you after the webinar to answer it via email. So thank you very much again to Erkan and David for the presentations today, and I hope everyone found it valuable.
Excellent. Thank you, Matt, and thanks once again, Erkan. Really good to have you with us.
It was my pleasure. I also thank everyone.